Alright, in this video we're going to look at a useful tool for solving a lot of equilibrium problems. And this tool is called an ICE table. So ICE tables are just a way of conveniently organizing our information when we work a problem. And we don't need ICE tables for all equilibrium problems. We've done a number of examples already where we didn't use them. How we know we're likely to need an ICE table is when they give us two sets of reaction conditions. So they tell us about the initial concentrations, and they tell us something about the equilibrium concentrations, and then they want to know more information. So when a problem's talking about both the initial and the equilibrium concentrations, that's when we're most likely to need an ICE table. And so the I row in the ICE table stands for initial. And so what we'll put in the I row of the ICE table are all the initial concentrations of each of the reactants and the products. The E row in the ICE table stands for equilibrium. And so in the ICE table, what we would put in the equilibrium row are the equilibrium concentrations. And then the C row stands for the change in concentrations. And so how we get from the initial to the equilibrium concentrations, that will give us the change. But the changes are all related, and they're related by the stoichiometric coefficients. And so if A is decreasing, if a reactant is decreasing, then products are going to be increasing. And C would increase by the exact same amount that A decreased. Whereas if A is decreasing, B is going to decrease by twice that amount. And when A is decreasing, D is going to increase, but by 3 times that amount. And so what we would put in the I row would be the equilibrium concentrations. So let me kind of write that in. And then the equilibrium concentrations, we'll have A at equilibrium, B at equilibrium, C and D at equilibrium. And then the change we often represent with the variable x. But the change, as we've just said, of all the reactants and products are related. So let's say that A is decreasing. Then if it's decreasing, I'm going to call that minus x, right? A is going to, whatever x is, we're going to subtract that from the initial concentration of A to get the equilibrium concentration of A. If we call A minus x, the sign on the change of B should be the same. If A is decreasing, then B is decreasing. So we'll call that minus 2x. And then if we called A minus x, the coefficient for A and C is 1, but now C is going to be increasing, and so we'll call that positive x. And D would be positive 3x for the change. And which side we make negative versus positive, let me put a plus in front of this x here too to emphasize that it's positive. We could just as easily had called A positive x and B positive 2x, in which case the products would just have the opposite sign. So the key is whatever sign the reactants have in your change row, we should make them all the same sign, and the products should also have the same sign as the other products, and that should be the opposite sign on the reactants. And then when I decided to make the reactants minus x and minus 2x, I was assuming that the reaction was going to the right. If I had known that the reaction was going to the left, then I think it would have made more sense to call these plus x and plus 2x and call the products minus. Now sometimes it's obvious from the problem which direction the reaction is going, so what to make the signs make sense, but it doesn't even matter. If we guessed wrong, then our x's are just going to come out to be negative, but as long as we keep careful track of our signs, it's not going to give us the wrong answer. So some other things that we can do with ICE tables: it is always true for any reactant or product that if you take the initial and add the change, that will be equal to the product. And that's true for any of them. Another thing that's true, if you take the initial concentrations and plug that into the expression for K or Q, that's actually going to give you a Q. Whereas if you plug in the equilibrium concentrations into the equilibrium constant expression, that's going to give you a K because we have the equilibrium concentrations. Now this has all been kind of abstract. I think it'll make more sense when we apply this to a specific problem. Now, before we do this problem, one thing I wanted to mention, textbooks often classify different types of equilibrium problems, and they sort of give them names. Something like this. I would actually encourage you not to worry about the labels that they put on these problems, right? Trying to remember, 4 different labels, 4 different types of problems, I think is not helpful. Just treat them all as ICE table problems. They're all just equilibrium problems. And then the steps that we need to take, you don't need to memorize anything. Just use your ICE table to figure out how to get the information that you need. All right, so here's the same problem again. I just gave us a little bit more room by reorganizing a little bit. And so here is our chemical reaction. And so we're told that the 3 gases were introduced to the container and they give us the initial partial pressures. And then they're told that the reaction reaches equilibrium, right? So we had these initial concentrations, then it gets to equilibrium, and they give us the equilibrium partial pressure of the NO2. And they want us to calculate the equilibrium constant. So my clue that I need to use an ICE table is the fact that they told me the initial concentrations and then told me an equilibrium concentration, and they also want to know the equilibrium constant. So since they're talking about both the initial and the equilibrium, I want to set up an ICE table. So let me rewrite the chemical reaction. So we have 4 NO2 reacts to form 2 moles of N2O and 3 moles of oxygen. All right, so then I have my I, C, and E rows. And they told me the initial partial pressure of the NO2 was 3.6 atmospheres. And for the N2O was 5.1. And then we have 8.0 for the oxygen. And then they also told me the equilibrium concentration of the NO2 was 2.4. And they didn't tell me the equilibrium N2O or the O2, but we're going to be able to figure that out. Right now, they want to know the equilibrium constant, right? So the expression for the equilibrium constant is N2O squared times O2 cubed over NO2 to the 4th power. But in order to calculate the equilibrium constant, I need the equilibrium concentrations. Right? Since these are not the equilibrium concentrations, if I plug this into this expression, it's going to give me a Q, not the K. And so I need to find the N2O and O2 equilibrium. I'm saying concentrations, but this problem is dealing with partial pressures. I need to find those equilibrium partial pressures in order to calculate the equilibrium constant. But we haven't filled in the change row yet. Right? And so for the change row, since the NO2 decreased, I know the reaction is proceeding to the right. And so I'm going to call the change in NO2 minus 4x. Right? I use the 4 because of the stoichiometric coefficient. And so if this is minus 4x, that means the change in N2O is going to be plus 2x, and O2 will be plus 3x. And we know that if we add the initial and the change entries for a given column, that will give us the equilibrium. So 5.1 plus 2x and 8.0 plus 3x. Now I don't know x yet. However, I can use the NO2 information to find x, because for the NO2, 3.6 minus 4x is equal to 2.4. Right? Again, I just added the initial and the change rows, and that has to be equal to the equilibrium row. And so when I solve for x, I'll subtract 3.6 from both sides. So I have minus 4x equals minus 1.2. Divide both sides by negative 4, and so I get x to be positive 0.30 atmospheres. All right, and I'm out of room, and so I'm going to just go on to the next slide. Okay, so I've just rewritten a lot of the information that we had before, and when I've rewritten the K expression, I've used the correct pressures instead of concentrations like I was doing before. Doesn't really matter, but better to be more correct. So in the last slide, we found that X was 0.3. And so now I can use that to find the equilibrium concentrations, or in this case, the partial pressures for the N2O and the oxygen. And so the equilibrium pressure of N2O is going to be 5.1 plus 2 times X. But we already found that X was 0.3, so that means the equilibrium partial pressure of N2O is going to be 5.7 atmospheres. Right? And the equilibrium partial pressure for oxygen is going to be 8.0 plus 3x. And so now we know the equilibrium partial pressures for all the reactants and the products. So we can go ahead and plug this into the equilibrium constant expression. So I have 5.7 squared times 8.9. Let me be consistent the way I write this. I'll put the exponents on the outside. So let's go squared, cubed, and then divided by 2.4. Let's write that a little bit neater. 2.4 to the fourth. And so then when I plug that into my calculator and evaluate it, I get the equilibrium constant is 690. All right, so I have several other videos with different examples, and they're all just different ways that we can use the ICE table problems. But again, don't try to remember what type of problem it is. Just know that when they talk about both the initial and the equilibrium partial pressures or concentrations, that we'll probably need to use an ICE table, and then just use the ICE table to organize your data to figure out how to go about solving the problem.